All right, so thank you, Gilad, for the introduction. I'm going to talk about WekaIO. I'm actually thrilled to talk here in Stanford about AI. So this year is the first year that this council also talks about AI. So I took the challenge of connecting what we're doing to AI. And Stanford, as you know, is where a lot of the innovation actually happened. And I have some quotes from Stanford researchers going on. So what we're doing, we are a fairly new file system, about 5 years. And our file system is the fastest file system in the world because we actually have the merge of two parallel file systems. So we're the only parallel file system over NVME, and then we have tiering to hard drive. So we have all the techniques that the traditional parallel file systems have when they're actually tiering. When they're writing to hard drives, we are actually tiering to object storage solutions. We have a lot of experience. We have a lot of partners. Actually, at supercomputing, we announced that HPE is OEMing our technology. So if you go now to HPE and you ask them for their high-performance file system, you will get WekaIO. We also have quite a lot of awards. So some quotes. San Diego Supercomputing has tested us on InfiniBand, and for some of their benchmarks, they've actually reached 100 times the performance they reached on their Lustre clusters. So they already saw a big advantage over their traditional ways of running things. DreamWorks is an HPE customer, and they're actually using us to replace their burst buffer technologies for their simulations, for their rendering. And actually what we're showing with WekaIO is that you have a fast enough coherent file system, there is no need for a burst buffer. So we provide higher performance than the current burst buffer for a real file system. Another quote that we have from TGen, where we're actually the only file system that they've found that they can scale their genomic workload. So they're used to, if you're running one workload on one computer, usually it's okay. A few computers, okay. At some point, their work becomes I/O bound. We've actually showed them that no matter how big they were trying to scale their genomic workloads, they remain compute bound. So the more servers they had, the work finished at about the same time, whereas they couldn't do it with any other file system. So now, let's go back to AI that we're somewhat familiar with what we're doing. Actually, people started thinking about AI in the 50s. So NATO was debating whether they should create drones. So why would you put fighter pilots on these airplanes and send them over? And back then they said, hey, it's going to be too expensive to create these kind of drones. They didn't realize they didn't have the compute power to actually do it. Reading that quote, actually, I wish I were 150 pounds, but their pilots are better than me. Going back to science, actually, Minsky is known as the father of AI. And he was saying in '67 that within a generation, the problem of creating artificial intelligence will substantially be solved. And actually, Minsky was right. In the 80s, within a generation from that quote, deep learning was found, and theoretically it was solved. Problem was that in the 80s and up until recently, there wasn't enough compute power and there was enough networking power to actually do anything with it, but it has actually changed. It has changed enough that even our legislators are now starting to talk about it. So I was in DC in November, and I was fortunate enough to hear Senator Peters talk about autonomous driving. He actually said that the US government realizes that 94% of the accidents are due to human error, and moving to autonomous driver is going to save 100,000 of human lives. So even the government realizes that artificial intelligence is very important, and they're actually going to push for it. All right. What does data, what does a file system have to do with artificial intelligence or with deep learning? Actually, so Dr. Pfeiffer is a Stanford doctor. She said that the more data that you have, and Imagenet actually helps enable deep learning. From almost 17 years ago, we can see one of the first research at Microsoft showing that the more data you have, the better your learning becomes. Actually, doesn't matter what kind of algorithm you're using. So you're going to improve your AI algorithms and your AI results with the more data that you have. Another Stanford researcher, Andrew Neig, actually created these very famous, very good for a file system diagram shows, a graph showing that the deeper the network, so the more layers that you have, the deeper the network, the more data that you need to actually to actually make it more efficient. So if you don't have a lot of data, you don't need a deep network, and then obviously you don't need accelerators like GPUs or the rest. But if you do have a lot of data, you do want to make your models more accurate, you can now create deeper networks, use these GPUs, and make sure that your training is done in an efficient way. What has changed recently? Because going back to Minsky, within a generation he was right, the science was there. What has changed recently is the GPUs, with the great help of NVIDIA, has helped condense compute. So we've just heard how even the national laboratories are going to use GPUs. It's very popular within the commercial world. So now most organizations make sure that they can have enough processing power to run these kind of computations. So there is enough network. EDR is prevalent. This year HDR is coming out. GPUs are becoming more and more prevalent. The problem is that with GPUs is that they don't get enough data. So when we go to talk with a lot of our customers, they see that their GPUs are idling, or they have problems scaling GPUs. So when they use traditional file system, they have 10 servers, it's okay, 50 servers, it's okay. When they get to the 100 or hundreds of servers, they cannot make sure that the data is served fast enough to these GPU servers. Also, NVIDIA, and these are NVIDIA graphs, is making a lot of improvement. The last generation actually improved 3 to 10x time between the P100 to the V100, and new generations are obviously coming all the time. So compute is now increasing every year quite a lot. We have to make sure that the storage catches up. When Gilad gave the introduction at the beginning, he said that AI and HPC are actually very similar, so let's look where are the differences. Why you may need slightly different system to support your AI, your deep learning application than your standard HPC storage. So you have to store and support vast amounts of data. When we look at autonomous driving project, the smaller project have dozens of petabytes, the bigger project have hundreds of petabytes, and as cars continue driving, these things only accumulate. So you need to be able to store vast amount of data, and you have to identify what you're going to train next, and you have to make sure that that data reaches NVMe fast enough while you're training the previous set, so you can start the next training session and have everything as fast as you can. You need high bandwidth but low latency, because you have tons of very small files. So the traditional file systems were very good at achieving throughputs of large files. But when you have voice samples, when you have text samples, when you have images, you have tons of files. Half a meg isn't small for them, and you would want to read sometimes line rate of these files. So you need to aggregate high throughput for a lot of very slow latency. Another thing is metadata performance really matters. They have huge directories. You need to be able to support billions of files in a directory, and these directories should work as well as small directories. Because when the cars upload the data, they don't care what directory they put it in. So it doesn't make just say, you can tell them, hey, split this file, like 1 million files a directory, just doesn't work. So they have to use a file system where 1 billion file or billions of files in directory is not a problem for it. And single host performance is important. So if these GPU servers, yep.
Is it more a POSIX file system you're looking for, or is it more object storage where you don't care about POSIX anymore? Or is it...
So the question was whether do you need a POSIX file system or an object storage would be enough. If it's okay, I actually have a slide on it, so I'm get there. But we see that you need both. So you actually, for some purposes, you need the object storage. For the other, you still have traditional thing that expect fully coherent POSIX file system. You need very high single host performance. The reason you need it because these GPUs, as we said, they condense their compute. You put 8 of these on a computer, so you can really fill up an EDR or dual EDR lines, and as you've just asked, multi-protocol, but we'll get to it. So what you get out of the WekaIO Matrix file system, it's a fully coherent POSIX file system with a faster than a local file system over NVMe. As you know, the traditional parallel file systems showed that a parallel file system was faster than a local file system over a hard drive. We're actually showing that we're faster than a local file system over NVMe. We have distributed coding. The bigger this cluster, the more resilient we are. We have very fast rebuilds, and we have end-to-end data protection to make sure the data has good enough integrity. You can take snapshots. They're instantaneous to take. They don't take away performance. We have tiering to S3, our second parallel file system, and partial file reiteration if you have large files, and then they don't all have the same heat map. We support InfiniBand or Ethernet, hyperconverged or dedicated servers, virtualized, Dockerized, or bare metal. Why does it make sense to create a parallel file system over NVMe? Actually, it took me some time to realize I need that graph because I thought it was obvious. But what you can see here is that when you're writing or reading from an NVMe device, it's within 30 to 100 microseconds. This is physics. When you send things over SDR, which is way over 10 years ago, it just takes 4 microseconds, even less. Over 100 gig, it's less than half a microsecond. So if you have the right networking stack, actually moving things around the network is a lot quicker than going in and out of the SSD. So now putting these SSDs on the network, aggregating them, creating a parallel file system over them actually makes sense. There are 2 ways that you can think about WekaIO installation. We can run in dedicated servers where the GPUs are connected through IB or Ethernet. Then we can tier to the data lake. You see a single namespace, so you don't have to care where the data is. If you just access the files, they will be there. Obviously, you can ask to stage for the next training session, or we can actually run the file system within the GPU servers, converging the solution. Now, to your question, you do need quite a lot of different accesses. So usually the ingest comes from object storage. Sometimes also SMB and NFS. Then there is a tagging or a cleaning phase. Usually these are HDFS-based programs. And then you have the GPU running. Usually, the programs that run them are POSIX. Obviously, looking for the files now is POSIX. People run fine. They're looking over contents of files, creating the next set. But actually, using an object storage-like interface would make sense. The problem with the current object storage interfaces is they're HTTP-based, and just converting the data with the base 64 is not as efficient as using a parallel driver that reads the data from many sources. So though you could actually use an object storage, a parallel file system client is more efficient. This is actually Imagenet that comes from here. The reason I put it here because it's problematic comparing data sets you don't know about to file systems you don't know about. But you can just download Imagenet 22K and run the traversals on your file system, see how fast it finishes. So doing an ls of a directory with the 21K files, either just the 21K different directories finishes in a bit over half a second. Traversing 14 million files is just a bit over 3 minutes. At one of our large customers, they compared us to a different file system that is perceived as the fastest. On the data set that they compared, that file system finishes the find in 6.5 hours, and we were just under 2 hours. So finishing the traversal in time or faster actually allows them to run a lot more sessions. And if you don't have to run find, there are other open source projects that finish the find process a lot faster. You want to be able to aggregate your throughput. If you have an EDR or dual EDR, HDR lines, you want to make sure they're filled, and you want to make sure that you don't need to cache. Because a lot of people, what they do, they have local NVMEs and they start by copying to the local NVMe, running on the NVMe. This is actually a waste of time. We are showing that even for a 4K, which we cannot parallelize, we provide about the same latency as the local file system over NVMe. And when you're accessing bigger files, we actually have higher performance because we can parallelize the access across many, many devices. And we can scale linearly. So you need double the GPUs, just double the size of a cluster. Actually, if you run hyperconverged, it just happens. So this is one example of real-time work that happened at one of our large customers. They had not such a big cluster, 10 nodes with DL360s and just 5 NVMEs. Actually, their current cluster is 4 times as big. And this is one of the leading current all-flash NAS vendors. They compared their application, and they saw that through NAS, they reached less than a gigabyte. Over a local file system with 4 NVMEs, they were able to get a bit over 3 gigabytes per second, and we provided 6.5 gigabytes per second. Obviously, we can read more, but the application has to pull it. This is actually hot off the press. So for the longest time, IBM said, hey, GPFS v5 is coming out. We'll get results better than WekaIO. So they just released their numbers about a couple of weeks ago over NVMe. So this is the GPFS v5 line. And we've used similar amount of NVMEs, but half the memory and half the cores. And while they reached 600 concurrent clients, we got all the way to 1,200. Also, they were using RAM caching. We didn't think it's actually allowed in the spec, but they got it through. We didn't use write cache over here, so we started with a little bit higher latency, but we were able to show that we scale a lot higher. We'll take it to the spec. If it's indeed allowed, we'll also submit results with write cache. Our tiering, as I said, we have a parallel file system over NVMe, but we also have a parallel file system over an object storage. So if you have large files, it's going to be chopped to a lot of small pieces and written to many objects concurrently, and also read for many the objects concurrently if you need it. If you know what is your next workload, we actually allow you to stage it in, though you don't have to. can just touch the files, read the data, and will bring it in from the object storage if it's tiered, though you don't want your GPUs to wait for it. So if you want, you don't have to do anything, it will magically work. If you want, you can actually stage your data to the NVMe tier. We have snapshots, 4K in granularity, redirect and write. Doesn't take any time to take them, and they don't take away performance because we redirect and write. And you can just take them. Unlike some other parallel file systems, they would rather you wouldn't take snapshot in high load. You can actually take a snapshot on the WekaIO whenever you want. But this is not the last thing of we have with our snapshot. Actually, we can take our snapshot and push them to the object storage with all of the metadata required to start a new cluster off of that object storage. We call that feature snap to obj. What do you get from that feature? If you're sharing a cluster, you get pause resume, because you can have your defined file system, take the snapshot, push it to the object storage. Now it doesn't have to be there. You can give the nodes to another workload. That workload will run. Then when you get more clients, you get less clients, you can just resume in whatever amount of new file system you want. You can have a backup. Actually, we have customers that use it as backup. We have customers that use it as hedge A, because you could just take a snapshot each hour. Then you can at least come back to the last hour. And cloud bursting allows you, similar to what you would do on a large shared network, actually, this is Amazon. You have your local on-prem cluster. You take this snapshot, you push it to S3. Anyways, it could be a global namespace. Now you can create a WekaIO cluster in EC2 as much as you want, double the instances, you will get double the performance, double again, you'll get double again. You work there. By the way, the original cluster can still work, all working on the same namespace, but with local latencies. You take another snapshot here, and you can mount that snapshot read-only on your original on-prem cluster, or you can create a clone of it. Now you can link to the results, or you can copy them back. All right, this is the explanations. Actually, all snapshots from all your clusters are just visible on the namespace, so you don't even have to be root to mount them. We have a very nice GUI. This was actually run in AWS. You can see that on the R3s, when we were running backwards compatible SATA code, we were reaching 10 million 4K reads for a customer on 300 nodes. All right, so summarizing what we saw here and how it helps AI machine learning, you can get full-line bandwidth. You don't need to cache, and you can burst to the cloud or share the same cluster with other users with a very easy ability to start and stop your instances. This is a list of our current features, lots of things I didn't describe. All right, I think I made it in time. Any questions?
Are all snapshots, is it for the whole file system, or can you do a subtree in the file system?
So our terms actually call all the aggregate of special directories on a cluster is called a namespace. By the way, our namespace supports trillions of files, so you wouldn't run out of inodes or these kind of things. Obviously, if directories support billions, the namespace has to be bigger. And then for us, a file system is just a directory that you can run some provisioning or management commands on. So a file system is subtree of the namespace that you can take a snapshot of. But you can have a lot of these, and you can take independent snapshots of them. You can actually have two clusters that only share a subset of their file systems. So you have one namespace on one cluster. You'll have a file system. You took the snapshot, you pushed it into the object storage. Another cluster has a different namespace, but it mounts that file system as a read-only snapshot or a read-write clone, so they're actually sharing a portion of the namespace. Did it make sense? All right. More questions? Yep.
Is this file system agnostic to hybrid clouds? I mean, like example, can I go partial AWS and partial Azure?
So the question was, can it run partially on AWS and partially on-prem? The way that our system works is that we let you run your workloads with local latencies. So you can have your on-prem cluster that runs locally. You can have a similar view of it, or the last snapshot view of it on the AWS. It will run locally. When you take snapshots on each other cluster, you can push them to the shared object storage. With AWS, it's mostly be the S3. And then all clusters that share a single ancestor can actually view these changes. So you can make changes on AWS, you would push them to S3, and your on-prem cluster will be able to mount them. And then the application, we don't do it because we're fully consistent coherent file system that runs on with local latencies. So we're not going to do these merge conflicts. But your application knows what you've changed in AWS, and then you can copy the data back locally.
So, is there data, is the use case involving data transfer between AWS and on-prem? Does that be prohibited?
So it's your decision. By the way, AWS is an example. Usually on-prem people have their own object store, and then there are no charges for data mobility. You can say, hey, I have enough NVMe capacity that I don't actually never have to read data back. So we support hundreds of petabytes of the NVMe layer if you can afford it. So it's your decision. Do we have time for more questions? Or? Any more questions? All right. Thank you very much.